Ghent University on the topic of offshore wind turbines. And my presentation is named Numerical Simulation of Laterally Loaded Monopiles, but I will not talk that much about numerical simulations. I will first talk about some generalities on the topic of offshore wind turbines, how they are designed. I will talk about some of the past research projects and some of the current ones. I will slowly dive into what kind of numerical modeling I am doing, and then I will finish by a conclusion. So first of all, what is a wind farm? It's how it's called. It's kind of a big area in the sea where you have a lot of wind turbines installed. So for example, here in Belgium, we have several ones that you can see on the top right screen. Wait, I will turn my pointer on. So several wind farms are currently installed. So the northern wind farm is actually 23 kilometers from shore, and they are operating since. There are many wind turbines that are planned because logically in the sea you have a lot of space, so you can actually have a lot of wind farms, but they cost money and they take a lot of time to get designed, get installed. So the current installed ones are these ones, and more are to come. So as you can see, a wind farm is composed of many wind turbines that are installed in special patterns, and one wind farm can actually be constantly updated with wind turbines. The number of wind turbines are not fixed. For example, here you can see some black dots, and then right after you can see some yellow dots. It's because the first phase of this project, they only installed few, and then they went into second phase and installed more wind turbines. So what is a wind turbine? Well, basically, the wind goes through the blades spin, and the generator converts the mechanical energy of the spinning into electrical ones. And obviously the wind turbines are all connected to what we call an offshore substation. Now the general rule is one offshore substation per wind farm, but I think it will change in the future. I don't really know. So the electricity generated is transferred through array cables to the offshore substation. Then this offshore substation goes and transfers the accumulated energy into the national grid. When we talk about wind turbines, the upper structure is more or less fixed. However, we have a lot of, how to say, room for the substructure. Now, the upper structure is made of a rotor that spins, the nacelle, the tower, and what you can see in yellow, the transition piece. This transition piece connects the upper and the lower structure. So here you can see in gray what we call a monopile foundation. There are many types of foundations, for example, gravity-based, tripod, tripile, jacket, and many more to come under research. But the most used form of foundation is by far the monopile. I think it's 74%, but I think these statistics don't take into account China. I think it can go up to, I think, 85% of the total foundations for wind turbines being monopiles. Now, there is a reason why people like this kind of foundations. Well, it's a little bit of the same as I said before. We have many type of foundations. And here, yeah, as I said, it can go up to 80% being monopile founded wind turbines. And the main reason why is that generally close to the shore, we have what we call a continental shelf that starts to dig down. The more you go away from shore, the deeper the sea goes. And right now, the most used or the most exploited regions are the kind of near shore. They're still quite far. For example, here in Belgium, 23 kilometers, 30 kilometers. But as you can see, as you can expect in the future, once these close to shore areas will be all exploited, people will go deeper and deeper in deeper and deeper seas, and we might see a lot of variation in the design. Now, a small word about how they are installed. All the components are carried on what we call an installation vessel. Now, this vessel in itself has a lot of geotechnics involved in it, because as you can see, the vessel goes into a desired location, it carries the pieces of the wind turbines, and then it goes into a jacketed mode. It lifts itself above the sea level on many legs. Now, there are a lot of variations. Here, I think it's 6 legs. I think other type of boats have 4. So there are a lot of boats out there. And as you can expect, as you can see, all the pieces are, it's not a monolith. So the wind turbine is made of different sub pieces that are assembled together. And for the installation, actually, I would say the boat needs to go to the desired location, and then the sub pieces are installed with the crane. And during this process, actually, the boat should be more or less perfectly stable. So there is I know that there is some geotechnical studies done beforehand to study the stability of the ship itself before the stability of the wind turbine. And when the pieces are assembled together, there is generally a small tolerance for error, so that the piece don't collide with each other during installation, and to not inflict damage to the pieces. So as you can imagine, the boat should be more or less perfectly stable. Now I talk about some of the loads that are applied on the wind turbines. So we say wind turbines, so the main source of load should be the wind. And because you have some wind currents, you also have some wave currents, you also have wave loading on the lower or medium part of the wind turbine. You have also, because you have a rotor, and the rotor has a frequency and it spins, so you have a rotor frequency that we call the 1P frequency, and to the rotor are attached generally 3 blades. So their frequency is 3 times the frequency of the rotor. We call them 3P. So overall, in their lifetime, wind turbines are subject to more or less 5 million loading cycles of wind, 400 million loading cycles of wave, 50 and 150 million cycles of 1P and 3P loading. Now, these loads actually have a frequency, as we have in offshore geotechnics. This chart is quite known. You have the frequency of the different loads, with the wind and wave being quite low frequency. Then you have the 1P rotor frequency, which is a range. And then comes the 3P frequency range, that is higher than the 1P by 3 times, so 3 times 1P. And then the question is, okay, I have a monopile. At what frequency do I want my structure to be? So we have what we call the soft design, where the frequency of the monopile should be placed here. But it's not a realistic design, because if you design your monopile to lie in this range, it would be very, very soft, and that is just yeah.
Not for you, Anis.
Sorry, no problem.
Yeah.
So what we call the soft range, where we put the monopile frequency, we design it to be in this region, it is not a realistic design scenario because it would be quite soft, unrealistic. We have what we call the stiff range, where we place the monopile frequency to lie in this range. Here it's the opposite. The monopile would be quite big size. That yeah, it's not economical for the overall project. So we have an intermediate range, what we call the soft stiff range, which is the most appropriate design range for the frequency of wind turbines. And obviously you want to avoid the forcing frequencies, because otherwise you have what we call resonance, which is a known phenomenon where you have dynamic amplification of the signal, and your structure will suffer a lot of damage if you place its lateral frequency in one of the forcing frequency ranges. Also, actually, there is another in the same, still in the same load stuff. We know that the frequency of wind turbines actually change with time. It can get stiffer or softer because your soil, which is the main contributor to the stiffness of the wind turbine, changes its frequency. So if you have what we call a strain softening tendency, it means that you have a loss of stiffness. You would perhaps want to put the frequency close to the 3P, because once your soil loses a bit of its frequency, it will go back to the left without entering the 1P. If you put if you put your frequency right close to the 1P, when the soil loses its frequency, it will go inside the 1P region, which is not optimal because it will suffer damage. On the other hand, you have what we call strain hardening tendency, where the soil gains stiffness generally after a lot of drain cycle of loading. So you would want to put your frequency right close to the 1P. So when the soil goes stiffer, it goes right, but without entering the 3P. So this is a known issue about the positioning of the frequency of the wind turbines. You have to be quite careful. And generally, you can't really tell how much it will stiffen or how much it will soften. So generally, the center is just fine. A bit about the limit states. Because it's a structure, it is actually designed exactly as you would design a pile or any kind of structure. We have more or less three main limit states: the ULS limit state, where you design your monopile or wind turbine to withstand severe storms or earthquakes, especially in, I think, the Asian region, where we have very big typhoons and stuff. There, the storms can be very, very scary. And I think also during these last years, we are starting to have quite strong storms in the North Sea in Belgium. The other type of limit state is the SLS, where you try to guarantee the serviceability of or the operational limit of your structure. And typically, we look at the deformation at the mudline level, at the soil level, where we try to limit the rotation and the deformation, because you can guess that you have a lot of load at the top of the wind turbine. And if your overall structure starts to tilt, you will have what we know in structure called as P delta effect, where the more you tilt, the more you go in. So it should be kept. Generally, we talk about 0.25 degrees or 0.5 degrees at the midline level. I don't really remember, but it's value at that range. Now, the for us in the North Sea, the designing condition is the fatigue limit state, the FLS condition. And basically here, what we do is that we try to control the eigenfrequency, as we told before, to lie in a specific range. And we check every part of the wind turbine against fatigue. So we use what we call SN curves. And these SN curves have been developed before for oil and gas platforms. And they are also used for monopiles. You can ask yourself, is it realistic or not? But you can adapt them more or less for wind turbines. So what we see is that the component of the wind turbine, for example, here, you have 59 millimeter wall thickness flush grounded monopile weld. And its SN curves tells you that, okay, if you want to withstand a certain number of loading cycles to failure, you should limit the stress to a point, to a given point. For example, here you have more or less 100, a cyclic stress of 100 MPa. This part can withstand this number of cycles. If it goes beyond this, it will fail. And as I said before, if you place your frequency of the monopile right on top of the forcing frequencies, you will have accumulation of damage and accumulation of amplification of the stress. So if you think, okay, I will have 100 cycles with amplification, you might have more than 100, you might have 200, and then it's not 1.3 times 6 cycles, it's way less. So if you design a wind turbine to be around for 20 years with dynamic amplification due to the eigenfrequency that is not well positioned, you might only be able to use your structure for maybe 10 years. And it is not optimal because economically wise, if you want to target a lifetime for your structure, you should either get to that lifetime or more. I will talk about how we can get more than just 20 years of operation later. Now I will dive a little bit on monopiles. They are actually huge structures compared to normal piles. They are generally used in the water depths of around 30 meters. But in the future, they will be placed in much deeper water levels, and it will pose its own challenges. But I will not talk about it now. Right now, the current diameter used for monopiles is between 5-7 meters. But in the future, and I say we kept saying the future, but the future is actually now. I think we are starting to see quite huge diameters, up to 10-meter diameter monopiles, and they are not a monolith. They are welded. You have small sub pieces of monopiles that are welded together. And as we know, the weld actually is a man-made imperfection. So if you need to check a typical place to be worry about is typically the weld, because it's an imperfection and you might have stress concentration in those regions. These monopiles actually carried on the kind of boats I showed you earlier, and they can either be hammered or vibrated into place. So if you want to install them to a designed depth, which is generally also maybe how much, maybe 10-20 meters below mudline level, they are hammered or vibrated, and these installation methods actually can inflict some damage to the monopile. Not that much, but I think if you design your monopile for 20 years lifetime, I've seen this in a research website. If you hammer them, you already consume 1 year of lifetime. It means you have inflicted more or less 1 year equivalent damage to the monopile. The monopile, once installed and once the wind turbine on top is fully installed, they generally suffer from what we call scour. Now, you have a region in your medium and water flows around your monopile, which might push away the soil from both sides of your monopile. Also, when the monopile is laterally loaded, it bends, so it also creates a bit of space between the soil and the monopile. We call this scouring. So to kind of limit this scouring, we install what we call scour protection system, where you have a small boat that comes and forms a small layer of rock around the monopile. It's called scour protection, and in simulations, they are modeled just as a small layer of soil surrounding the monopile. Now, we have a lot of uncertainty about this scour protection. We don't really know how it contributes to the overall monopile behavior, because you can imagine that you have small stiffness contribution at this level because you have soil. So it is open research. How monopiles are designed in design firms up to, I think, 3 or 4 years earlier, they were still using what we call the API PY curves, API/DNV, different recommendations. But they use the same method. You discretize your soil medium as being a set of springs along the monopile, and you have reaction curves, and then you laterally load your monopile, and you know what stresses you have in your monopile. Now, these API or DNV methods have been developed for offshore platforms, for oil and gas platforms, where we use piles that we consider to be flexible. Now, the typical diameter of an offshore gas platform, I think it's around 1 meter, maybe 0.8 meters, which is nowhere near the monopiles. The monopiles are a lot bigger in diameter and a lot shorter. So overall, they have a smaller bending stiffness, E times E, EP times IP, compared to the regular flexible piles. So the question of applying these design methods to the monopiles is actually open, but now we know that they are not really applicable. If you use this kind of reaction curves to design your monopiles, you will be a lot away from reality, which motivated few research projects, namely the PISA research project, where they performed real scale tests on large or comparably large piles as the one used for monopiles. And they came up with few recommendations. They also introduced 4 reaction curves attached to the monopile compared to only one with the API recommendations. And they are based on field tests, numerical models, and 1D models. Now, the story behind this is that you perform a load test on scale. You try to back model these field tests, get it to match. Once you match, you extract your curves directly from the 3D finite element model. it's quite easy to do. I think there is also a software or a Praxis version called Praxis Modeto that does this for you. You perform numerical models and then you extract the reaction curves from this 3D model. And you want to do this because if you have 40 or 50 wind turbines in a wind farm, performing 3D advanced numerical models for each of the pile can be quite challenging. These kind of models are easy to do and quite fast. And so they are better liked in the industry. In the project I'm working on, we have access to years and years of monitoring data on real scale monopiles. So the real monopiles that have been installed in the Belgian North Sea have been monitored for years. And we have access to that monitoring data. So the monitoring system actually is composed of accelerometers, strain gauges, and fiber Bragg gratings on the substructure. So using these fiber Bragg gratings on the substructure, you have strain measurements that you can convert to bending moment measurements. So the idea is to use these monitoring data to constantly tune our models to match what we see in real time. So you have a 3D model, you have reality, and then you come up with some scenarios that can explain or help you to match what you see in real time. And what we see with our monitoring data is that when we design a monopile, however we design it using the old or the new methodologies, the as designed frequency is always lower than the as monitored frequencies. It means that the monopiles that are in field, they are stiffer than in our models. So when we model monopiles, we are actually quite conservative because they are stiffer than in the models. And obviously we want to address that because in offshore wind energy, conservatism means you spend a lot of money, and also it means that afterwards the energy that comes from those structures will be higher. So if you want to bring down the cost of energy, you need to bring down the cost of offshore wind turbines. And also because in offshore wind energy, as I explained earlier, over design doesn't mean safe. I know that in structural engineering, maybe you over design, even if it costs a lot, but you can say that you are more or less safe. And it is the method or the methodology that has been used in oil and gas platform design. You just multiply by a huge factor of safety and then you over design and then you're safe. But for wind turbines, as I said, you are surrounded by forcing frequencies. So if you over design, you might fall into a forcing frequency region where you will have accumulation of damage due to resonance with the forcing frequency. Now a bit about numerical modeling. This is a typical monopile model. So I use Abacus to model the monopile. I also fully scripted my models, so I don't have to re-click my way through the model every time. So this model is meshed and generated and meshed, and parameters are assigned quite fastly using Python. And for the soil modeling, we go to the hypoplastic models, which are, in my opinion, more advanced than the hardening soil models, the hardening soil model. I think you should choose the appropriate constitutive model for your work. And it doesn't mean that the hypoplastic model or the hardening soil model is not good. It's just that some models do some stuff better than others. For example, for the hypoplastic models, they are quite stiffness tuned. It means that you can control the stiffness. You have a lot of parameters to control the stiffness only. And that is quite what we need, because stiffness of soil means stiffness of offshore wind turbines, which will lead you to the fatigue limit state control. So the starting point is obviously the calibration of your constitutive model. So we have access to the design reports of all of the wind farms, and we also have access to the laboratory tests that were performed. They range from Bender element tests to cyclic DSS tests. And the main parameter that we are looking at is actually the Gmax, or soil stiffness, because at SLS or FLS conditions, you are at relatively low strain. So the strain around your, the soil strain is around the initial Gmax. Also, you might have a small degradation due to cyclic loading, but they are generally quite small, relatively close to Gmax. This is why we look at Gmax. And this is an example of calibration of our constitutive models, where you try to fit the measured Gmax using Bender element test in your hypoplastic model. So for example, this kind of curves I produced for a paper that I'm publishing right now, but they come with their own difficulty, because when you have monitoring data on a monopile, you have to kind of use it. And for example, the wind turbine I'm looking at is located in a 6-layered soil. So I had 6 layers of soil for which I had to calibrate the constitutive models one by one. So it was, I think, sand on top of clay, on top of sand, on top of clay, which is quite challenging. And the typical result we see when modeling wind turbines. So for example, for this work, we derived 11 load cases ranging from load case 0 to load case 10, but I am only showing 3 load cases here for clarity. So we had load cases where we used the meteorological and SCADA data and all of that to derive loading on the monopile. We load our numerical models and we compare the simulated and the monitored bending moments to try and gain insight. What we see is that for all the load cases, the simulation bending moment is always more than the monitored ones. This means that the soil surrounding the real monopile is stiffer than in our models, or the wind turbine is stiffer. It's better to say wind turbine is stiffer, because the stiffness of wind turbine is not only soil. So this is actually something we see quite regularly. It means that we are somehow over designing our monopiles, and we have room for how to say, optimization. And the monopiles are laterally stiffer than expected. It is either because we are underestimating the actual soil stiffness through our calibration. Maybe the soil is stiffer, even if we measure some stiffnesses, like I tried to calibrate my model before. But even doing that, I think we are still maybe underestimating the actual soil stiffness. There is also another factor, which is the installation effect of the monopiles when they are vibrated or hammered. We didn't take those into account. And we know that if you hammer or vibrate your monopile through the soil will go into some sort of consolidation, and then it will have an increased stiffness due to the increased effective stress surrounding the monopile. And last, what we are also looking at is that the small scour protection system that we never really modeled, it maybe has a lot of contribution for the lateral stiffness of monopiles. So maybe if we model the scour protection, or we include it in our models, maybe we will be able to close this gap. And this work is actually being done right now. So as a conclusion, what we see through our measurements is that offshore wind turbines are stiffer than designed, stiffer than as expected. We can further optimize the wind turbine design by closing the gap between what we see and what we measure. And this will bring the cost of offshore wind energy down, hopefully. And overall, more research is needed to identify all the contributors to and their magnitude to the lateral wind turbine stiffness. So that's it for me. Thanks for your attention.
Great job.